Alrighty, so this video we're going to be talking about the most important idea and concept you will learn in physics. And the reason this is the most important concept is because, as I stated in a previous lecture, pretty much everything you ever do in physics involves vectors. So if you don't understand what vectors are or the rules by which you manipulate vectors, you're not going to be able to solve very many physics problems at all, even the most basic physics problems. So it's very important that you understand this concept and you practice it a great deal so that it becomes second nature to you. After a while, you won't even have to think about it. It'll just be natural in how you mess with vectors. So first thing we need to figure out is what is a vector, of course. And it's actually a mathematical idea. We started, and when people go through mathematics and go through science, the most basic quantity a person or a scientist deals with is what's called a scalar. And a scalar just is like a magnitude or an amount. How much? So for instance, if you ask how fast is this person going, you might say they're going 10 meters per second. That's a speed. A speed is what's called a scalar. 10 meters per second, let's say. It's basically saying how fast, the magnitude of their speed, how much. Or you turn on the Weather Channel and you look, what's the temperature outside, and they say it's 85 degrees Fahrenheit. So temperature, that's also a scalar. It's telling you what is the temperature, the magnitude of the temperature. And that's fine. In fact, there's a lot of things that could be considered scalars. What they all have in common is at the end of the day, they give you one big piece of information, and that is the magnitude of the quantity you're talking about. Now, over time, of course, scientists, mathematicians, started messing with these quantities and figured that just like if you were to start with basic problems, you might say, okay, here's the x-axis. Here's 0, 1, 2, 3, and so forth. And you might have a particle here at the 0 location, and it moves over to the 2 spot. And then maybe it then moves back to 1 and so forth. You're describing its motion in one dimension. It's moving left and right. It's one-dimensional, only the x direction. And that's perfectly fine. But of course, one can modify this and say, well, look, there's also a second direction an object can move in, and that's the y direction. And so maybe instead of just moving left and right, maybe once it hits this place at 1, it then moves up to 2, and then maybe it moves over to 3 downwards like this, and so on. Now all of a sudden you have something moving in 2 dimensions. And of course we know in the real world that we live in, there's 3 dimensions of space, and so on. So mathematicians really enjoy generalizing problems, and when they started talking about dimensions, knowing that there's more than one dimension to speak of, they generalize to multiple dimensions. Now they go more than 3 because that's what mathematicians do. They could go up to an infinite amount of dimensions and so forth. But at the end of the day, by going up in dimensions, there's more information that need to be relayed. For instance, if I want to know if this is where the position of the ball is or whatever object's moving, and I want to say, where is that thing? I can't just give you one piece of information. I say, well, it's 1 meter in the x direction, and then it moves up 2 meters in the y. So I would say the position of this object is in kind of a coordinate pair type thing. It's 1 meter in x and 2 meters in y. So I have to give you two pieces of information because we're in 2 dimensions. And of course, in 3 dimensions, I'd have to give you 3 pieces of information, and so forth. Well, this led to what's called vectors. Instead of giving 2 pieces of information like this, I can say the position is one thing. It's the position of the object. And that position is, I go a certain amount from the start, and it's at a certain direction. Now, there's still built into this thing called position 2 pieces of information, how much in the x direction, how much in the y direction, but I can think about it as one single object, the position. That, at the end of the day, is what vectors are. Vectors, in the most general sense, are these arbitrary quantities that instead of just telling you one piece of information, the magnitude, it gives you 2 pieces of information. They tell you the magnitude as well as something extra, which is the direction. So, an example related to the speed is what's called the velocity. So now when someone says, oh, that person's moving at 10 meters per second, they could actually give me the velocity, which is more something like they're moving at 10 meters per second east on I-10 or something like this. So they're telling me not only how fast they're moving, but also in which direction they're moving, because that's helpful. If someone's moving to the left versus someone moving to the right, that makes a big difference in where they're going. So not only knowing the magnitude is important, but also in which direction this magnitude points. Temperature, of course, that's a scalar. There's no such thing as how hot is it outside? Oh, it's 90 degrees northeast. That doesn't make any sense. It's 90 degrees and that's it. There's a magnitude, that's a temperature. So not everything is a vector. In fact, speed is a scalar because the speed only tells you the magnitude. Velocity, however, may say 10 meters per second to the east, or something like this. That's the vector version of speed, and it's called velocity. Another example could be like the wind. So again, you turn on the Weather Channel, and a lot of times you'll see a little map, local map, and it'll have arrows and numbers next to the arrows that represent how fast is the wind blowing and in which direction the wind is blowing. So, you may have wind direction. You may have something on the map that looks, this is the direction of the wind and it's blowing at 5 miles per hour. So again, this gives you a magnitude, the 5, how fast the wind is blowing, but also the direction, in which direction the wind blows. Is it blowing in from the north or towards the north or whatever? So this is nice. All of a sudden, there's this kind of abstract idea of a vector that allows us to think about multiple pieces of information as one single object that could be manipulated. This allows us to manipulate 2 things at once, basically. Now the problem is when mathematicians invented this idea, of course, they found that the mathematics that used to work for scalars, addition, subtraction, multiplication, things like this, don't necessarily work for vectors. We would have thought, well, math is math, adding things is adding things, and so if I want to add vectors, well, I just add them the same way I would add numbers. So for instance, if I have speed for A is 10 meters per second, and then the speed of B is 5 meters per second, I could say A plus B is 15 meters per second. This would be something like there's a little car here, let's say, moving to the right at 10 meters per second, and there's a person on the car holding a baseball, and they throw the baseball at 5 meters per second with respect to themselves. Someone outside looking at this measures the speed of this baseball not as 5 meters per second, but as 15. Because if the person throwing the baseball didn't throw it at all, was just holding it, then the person outside would see the baseball moving the same speed as the car, 10. But if the person then throws it an extra 5 meters per second, it's moving at 15 meters per second now. That's adding scalars. You're just adding two numbers together. However, a problem comes in when you have something like this. Let's say there's a car, and now this is kind of a top-down view, and the car is moving northwards with a speed of a velocity of 10 meters per second to the north, and the ball is thrown this way with a velocity of 5 meters per second east. Now someone outside looks at that ball. How fast are they going to see the ball moving? Well, it turns out they're not going to see it moving at 15 anymore. And this is the problem with adding vectors. You cannot add vectors to get an answer the way you would add scalars. In fact, the rule of mathematics says you can only add two vectors together if they are in the same direction. Well, that's pretty bad. Because pretty much everything we're going to be doing, objects move in different directions. It's rare that two objects are going to move in exactly the same direction. So, because of this, there's a new rule that must be implemented. And we're going to go through this rule. However, before we do, I want to go through a little bit of trying to visualize better what a vector is, or how it's represented. And so we're going to talk about the graphical representation. So we know how to display scalars. They're just numbers, so you just write down a number. That's fine. But how do you display a vector if it's two pieces of information? Well, the first thing is every vector, if it's written out, if it's not typed in a textbook or something, usually is denoted to be a vector by a little arrow on top. Now, I put just one single line over it. Some people put double line to make the arrowhead. But basically, the variable with an arrow above it tells you this is a vector. And the reason is because we can't write in boldface. In a textbook, generally speaking, vectors are written in bold. But when written out, on a board or on paper, we represent a vector saying this thing is a vector by putting a little arrow overhead. Now, there's different ways of representing it, but in terms of an easy way we could think of, we talk about what's called the magnitude. So this symbol here, this is absolute values symbol. And the R inside is the number. So that may be, as an example, 10 meters per second. So that's the magnitude of, let's say, A being the velocity. I throw a ball in a certain direction. I give it a speed of 10 meters per second, and it's thrown in a certain direction. That's represented by an angle, theta, in general. So R is the magnitude, how fast. Theta is direction, maybe 30 degrees north of east. this would tell us someone threw a rock. The rock was thrown with this speed, 10 meters per second, in this direction, 30 degrees north of east. If I were to try to draw this out to visualize it, it's very easy. Here's the x direction, here's the y direction. Well, the velocity is going to be an arrow. Any vector is drawn like this. It's an arrow that always starts at the origin. The length of the arrow tells you about the magnitude. Now, of course, in general, we have to do this scaled down. I'm not literally going to draw a 10-meter long arrow. So let's say the length of this arrow here is representing 10. So maybe it's 10 centimeters or 10 millimeters or whatever it is, but it represents 10 meters per second. And notice that I drew the arrow pointing in a certain direction, and that's because what I did was I said, okay, from the x-axis, the east, I went 30 degrees north of that. So this angle here is 30. So, graphically, this vector A is shown as an arrow. The arrow starts at the origin. It points in a direction given by theta, the 30 degrees north of east. That means start on east and goes 30 degrees north of that. And so that's what this is. And then how long should this arrow be? Well, I'd get out my ruler or whatever, and I draw it 10 millimeters, 10 centimeters, whatever I want my scale to be. And that's my vector A. Vector A. And that's how you represent graphically vectors. Pretty easy. If I have another vector, let's say I have vector B, and let's say that's 20 meters per second, and this is going to be at let's say 30 degrees west of north. Okay, so how do I draw this? I say, okay, west of north. So I start on north, and I'm going to go 30 degrees to the west. So this is going to be about 30 here. And now the length of my arrow is 20. Well, that's twice as big as arrow A. So however big arrow A is, I need to draw B twice that length. So something like this. 20. Okay. So it's not too bad. The length of the arrow is the magnitude. The direction the arrow points is given by the theta, the direction. And that's how we're going to do graphically. Now let's say I want to add these two vectors together. Well, there's a certain rule to do this, and so if I'm going to do this graphically, which in general we're not going to do it in this class graphically, we're going to do it analytically, mathematically, but I'll show you how to do it graphically. What you do is I'm going to use what's called the tip to tail method. And what it says is, look, I've got my two vectors, vector A and vector B. Take one of the vectors. It doesn't matter which you choose. I'm going to choose A. Take this vector A here, and you're going to slide that vector, keeping it parallel to itself so you don't rotate it or anything, and you just move it so that the tail of vector A, that's the starting point, lies on the tip of vector B. So if I were to redraw vector A on the tip of vector B, it would look something like this. Right? I took vector A, I slid it to the tip of vector B without rotating it, and I redrew it there. So now here's my fake vector A. And now, the last step is to just draw a new vector. Of course, all vectors start at the origin. And you draw the vector, the arrow, from the origin to the new tip that you just drew, the end of this new vector A. So there it is there. And the answer to C, which is the sum of A plus B, is this red vector, this red arrow. And in order to figure out what it is graphically, you take your little ruler and you'd measure, okay, how long is this arrow? And then you compare it to the scale you used for vectors A and B, and you get some number. I don't know, maybe it's, let's say 21 meters per second or something. I'm not sure what it is. But it's some new magnitude. And the direction, you just use a compass to find the angle that this new vector makes with respect to the axis. So maybe it's at, I don't know, 5 degrees west of north. Don't take these two numbers seriously. It's just I'm eyeballing it. I know I didn't do it accurately, but the method is what's important. That's how you add vectors together if you're going to do this graphically. So, vectors drawn, you start at the origin. You're going to draw an arrow whose length tells you the magnitude. And that arrow has to point at an angle. The angle is given by the direction of the vector. Every vector must start at the origin. So I have two different vectors here, A and B. So I drew A first, and I drew B second. And then this vector C that I did here, what does it represent? Well, imagine I gave you this question. A person walks with a speed of 10 meters per second at an angle of 30 degrees north of east. Then, while walking, they are pushed, giving an extra velocity of 20 meters per second at 30 degrees west of north. The question is, how fast are they now moving? Or maybe this is a boat on the water. The boat is traveling, the boat's just sitting there, and the tide or the current in the water is pulling the boat with a speed of 10 meters per second at an angle of 30 degrees north of east. Then the person in the boat driving the boat turns on the engine and sets the engine to give them a velocity of 20 meters per second, 30 degrees west of north. Of course, the current is still affecting them. So there's two different effects happening to this boat, and I want to know what's the final result? What's the final velocity, and in which direction is this boat moving? The way you answer that question is you say, okay, I've got a vector A, the speed because of the current. I've got a vector B, the velocity because of the engine. So the total velocity is just the sum of those two vectors, vector C, and we see how to do it graphically. Okay? This is a general rule. Just like over here, previously, when I had the car is moving 10 meters per second, the person throws the ball 5 meters per second from the car, and it was quite evident that all you do to see the total speed of the ball was add the two speeds. The same is true here. There's two velocities affecting this boat. If you want to know the total velocity, you add the two velocities. The problem being that these are velocities, which means they're vectors. So it's harder to be able to add them. It's not just adding numbers, you're adding vectors. But we see how to do it graphically. Again, we're not really going to do the graphical method because it's time consuming, and then you need the tools. You need a ruler and a compass or a protractor, and we're just not going to deal with that. So instead, we're going to talk about analytical methods, which means how do we do this with mathematics? So let's start again. Let's say we have our two vectors. Here's vector A, and let's say that's 10 meters at 30 degrees north of east. And then vector B is 20 meters at 30 degrees west of north. So now we're not talking about speeds. Let's say we're talking about, or not talking about velocities, I'm sorry. We're talking about positions, distances. I want to be able to add these two things. So let's say the question is this. A person starts walking from their front door ten meters at an angle of 30 degrees north of east. They then turn and walk an additional 20 meters at an angle of 30 degrees west of north. How far from their front door are they? Okay. So let's say that's the question. We're given two vectors. First vector, they start from the front door, and I can draw this out. Here's the front door, the origin. And they walk out 10 meters at an angle of 30 degrees north of east. So that's something like this. Here's my vector A. 10 meters, and this is 30 degrees. The second vector, vector B, they go 20 meters, 30 degrees west of north. So that's something like that. 20, this is vector B, and this is 30 here. And if they do those two things, where will they end up? Of course, when you think about what the person's actually doing, they walk vector A, and from vector A, they then do vector B. Right? They go 10 meters at this angle, and then 20 meters at this other angle. And they end up right there. And I want to know how far from the origin, how far from their front door, is that location. Okay? So again, you can see we're adding two vectors together to answer this question. But I don't want to do this graphically. I want to do this analytically. The problem is, I already told you, mathematically speaking, you're not allowed to add two vectors together unless they're in the same direction. And you can see vector A points in this direction, vector B points in this other direction. They're pointing in different directions, so I cannot just add them. I can't say vector C, which is A plus B, is 10 plus 20, which is 30 meters. This is wrong. So we need to think a little bit more creatively about this problem. The rule of mathematics says you can only add two vectors if they point in the same direction. But they're not pointing in the same direction. However, what we could do is this. Let's look at vector A by itself. Here's vector A. 10 meters. Here's 30 degrees. Notice vector A, to get from the origin to where vector A ends, that 10 meters, I could either follow the line of the arrow, or I could do something else. I can go a certain amount in the x direction, and then a certain amount in the y direction. So, there's two ways of getting to that point. Either follow the straight line, which is 10 meters long, in this certain direction, or the other thing I can do is I can go a certain amount in the x direction, and I'll call that amount ax, and then a certain amount from that point in the y direction, ay. Either way, I'll end up at the same point. And notice I could do exactly the same thing for vector b. Here's vector b, 20 meters. This is 30 degrees. Notice that if I want to get to this point, the end point from the origin, I could go a certain amount in the y direction, call it by, and then from there move to the left a certain amount in the x direction, bx. And again, I'd reach the same point. If I think about this, then what I can do is something fancy. I can say, well, instead of trying to add vector A and vector B together, since they're not pointing in the same direction, let's look at what's called their components. The components meaning how much of my vector A points in the x direction, and how much of my component A, how much of my vector A points in the y direction. So that's called the x component and the y component. And this is good because if I do that, then I can say, look, vector C, whatever vector C is, he will also have an x component and a y component. And I know, just from logic, that the amount moved in the x direction for C is how much did I move in A plus how much did I move in B in the x direction. So to get Cx, I just take how much did I move in the x direction by A and add it to how much did I move in the x direction by B. And the reason I can do this is because the x component of A is the x direction. The x component of B is also the x direction. So they move in the same direction. And now I can follow the rule of mathematics. I can add those two things because they are in the same direction. And of course, the same holds for y. The amount of C, which points in the y direction, is just how much did A move in the y direction plus how much did B move in the y direction. So we're doing a trick. Instead of adding A and B themselves, I'm going to break A apart into two pieces, AX and AY, and then I'm going to break B apart into two pieces, BX and BY. And then I can get my final C by saying the X piece of C is the X piece of A plus the X piece of B. And the same for Y. The Y piece of C is the y piece of A plus the y piece of B. So, let's see it in action. How do we actually do this? Well, let's look at A again. Here's vector A. 10 meters. This angle is 30 degrees. And what I'd like to know is how much of A points in the x direction. And then I would like to know how much of A points in the y direction. Well, notice what I have here. I've got a right triangle. I've got a right triangle where the hypotenuse is 10. This angle is 30. I know this is my right triangle. This side I'm calling AX, and this side I'm calling AY. And now we see where trigonometry is going to come into play. That's why we had a review trig last week. I'm going to use the tricks of trigonometry to be able to find these two sides of my triangle, AX and AY. So how do we do it? Say, okay, well, let's say I want to find AX. Say, okay, well, this side here, the AX side, that side is either opposite or adjacent to the angle theta. Well, here's the angle theta, the 30 degrees. This side is right next to the angle, so it's adjacent. And SOHCAHTOA says if I have adjacent, that goes with cosine. And if you remember what ca meant, it says cosine of theta is adjacent over hypotenuse. Well, notice I don't want cosine theta. What I want is the adjacent side. I want the AX. So I'm solving for adjacent. So let me solve this little equation for adjacent. In order to do it, I multiply by hypotenuse, but I have to do it on this side too. And it tells me the adjacent side is the hypotenuse times cosine of theta. So I look at my triangle, I say the adjacent side, AX, is the hypotenuse, 10, times the cosine of theta, cosine of 30. And I now have a mathematical equation. I use my calculator, and it tells me how much of vector A is in the x direction. That's called the x component of A. So what does this turn out to be? This turns out to be 8.66. I now have the x component of A. What about the y component? I do exactly the same method. AY I'm looking for now. Here's AY. Here's the side there. That side, is it adjacent or is it opposite? Well, the angle theta, 30. AY is the side opposite to it. Opposite goes with sine. And I say, okay, sine theta is opposite over hypotenuse. And the same way, if I want to solve opposite, I get opposite is hypotenuse times sine theta. Exactly the same way as before. So again, I go back to my triangle. AY, that's the opposite side, is the hypotenuse, 10, times sine of theta, sine 30. There we go. There's my little calculation to find the y component of A. Plug that in my calculator. That tells me the answer is 5. And now what I've done is the very big important thing called I broke my vector A into its x and y components. So breaking up a vector into its components, this is how you do it. Every vector is going to have an x component and a y component. You draw the vector out, put your little magnitude and your direction in the triangle the way it's supposed to be, and then you look at the triangle and you use trig to find out the components. Do not, as I said when we talked about trigonometry, Do not just memorize x component goes with cosine, because that's not always true. It's true for this one, but it may be opposite for another problem. Don't memorize x is cosine and y is sine. Instead, look at the triangle and use SOHCAHTOA to tell you, is it cosine or is it sine? Anyway, there's vector A components. What about B? Let's do the same for B. Here's vector B. Length of 20. This angle here is 30. And again, what I'd like is the x piece, bx. X is always the one that moves left and right. And a y piece, vertical piece, by. And just as before, I'll just draw the triangle out over here so we can see it as a pure triangle. Okay. All right, here's my hypotenuse, the length of 20. Here's the right angle, and here is the direction 30 degrees. This is the by side. This is the bx side. And now we want to do exactly the same thing we did for A. I want to find bx and by. Oops. By is green. Sorry. All right, bx. Here's the x side. That's the horizontal one. Is that adjacent or opposite to my angle of 30? This time, x happens to be opposite to 30. Okay, again, going back to SOHCAHTOA, opposite goes with sine. So, just like I have here, it's going to be hypotenuse, in this case 20, sine of the angle, which is 30. However, we have to be very, very careful here. This is almost the answer, but not quite. Notice our vector here is pointing up and to the left. That means the x piece of this vector is pointing leftwards. Before, for vector A, our vector A pointed up and to the right. So his x piece was pointing to the right. And in general, we say the direction right is positive and the direction left is negative. Just like we would say up is positive and down is negative. So because of that, we have to be careful to note here for this vector, since vector B points up and to the left, the x piece means left, and left is negative. So we have to put a little negative sign on him. Okay. Vector A's x component was positive because vector A pointed to the right. And rightwards in the x direction is positive. And also notice we're using sine for the x piece. So just like I said before, don't memorize x is cosine and y is sine, because here we have an example where it's not. In this case, the x piece is sine. The best way to remember this and to not get it confused is to just look at your triangle. If you look at your triangle, you see where is the x piece. There's the x piece upstairs. That side is a side opposite to the angle, and opposite goes with sine, SOHCAHTOA. So, plug this in my calculator. Negative 20 sine 30 means negative 10. What about the y component? Okay, well, here's the y side over here. That's the vertical side. Is that side opposite or adjacent to my angle of 30? Well, the y side is right next to the angle, so it's adjacent. SOHCAHTOA says adjacent goes with cosine. So I'm going to say 20 cosine 30. Then I ask myself, is this positive or negative? Well, vector B pointing up and to the left. In the y direction, he's pointing upwards, and upwards is positive. So he's positive. So don't be confused that because x is negative, y has to be negative. That's not true. X and y are independent from each other. So in this case, x pointing to the left, negative, but y is pointing upwards, so he's positive. So plug 20 cosine 30 into my calculator. Again, remember you're using degree mode in case you're not getting these numbers. And you get 17.32. All right, good. So now what I've done is I have vector A and vector B broken up into components. Vector A has an x component, which was 8.66, and a y component of 5. Vector B had an x component of negative 10, and a y component of 17.32. And remember what we're trying to find. We're trying to find vector C. We want C, which is A plus B. But we couldn't do it directly. So what I can do is I can say, okay, well, I don't know C, but I can get the x piece of C. And the x component of C is just going to be the x component of A plus the x component of B. Okay, well, that's not so bad. 8.66 plus negative 10. Plug that in my calculator. And I get negative 1.34. And in y direction, well, the y component of C is the y component of A plus the y component of B. So what do we have? 5 plus 17.32. And we get 22.32. Nice. We're really, really close to being done. What we have here are the x and y components of my final answer. However, what I want is a vector. I want magnitude and direction. How can we get this? Well, let's look at what this vector looks like. What does C look like if I were to draw it out? Here's C. I say, okay, I go, the x piece is negative 1.34. That means in the x direction, I go to the left 1.34. So there's that. And then the y component, I go 22.32. So that means in the y direction, I go upwards 22. So that's way, way, way up here somewhere. Okay, so now all I do is I draw a line, a vector, which starts at the origin and goes to that new point up there. There we go. Okay, let me just clean this little guy up because obviously we're going to need this in a little bit. So there's the x piece and the y piece. All right. So this is the vector C I'm trying to find. This red line here. I want to know what is his magnitude C and what's his direction theta. What do I have? Well, I have the x component of C is 1.34 negative, and the y component of C is 22.32. What do I want? I want this side, the actual vector, the magnitude, and I want the direction theta. How do I get it? So look at what we have. We have a right triangle. This side is C. Here's the y component. Here's the x component. I know this is 1.34, and I know this 22.32. Call them negative, of course. So again, we have a trig problem. Here we have a right triangle. Only this time, we're trying to find the hypotenuse, and we're trying to find the angle. So how do we use trig to do that? Well, the hypotenuse we know how to do. If I want the hypotenuse, but I know the length of the other two sides, I use Pythagorean Theorem. And Pythagorean Theorem says c squared is a squared plus b squared, right? So that means c, the hypotenuse, is the square root of the x component of c squared plus the y component of c squared. That's like calling this a and b. A squared plus b squared equals c squared. A, though, is the x component, and b is the y component. Nice. So all I have to do is plug the numbers in. So x squared, that's negative 1.34 squared. The whole thing is squared. Plus the y component, 22.32. That thing's squared. And now I stick this in my calculator. And when I do that, I get 22.36. Okay, what is this? This is the magnitude. That's half my answer. Remember, what I want is magnitude. C vector is magnitude of C and the direction. I now have the magnitude. How do I get the direction? That's how do I find this theta? Well, what do we know? We know this side, the x component, and we know this side, the y component. That means I know if I'm looking for theta, I know the opposite side, and I know the adjacent side. And I know from SOHCAHTOA, tangent of theta is opposite over adjacent. Okay, so if I want theta, that means theta is inverse tangent of the opposite side over the adjacent side. And now I just plug the numbers in. Theta is inverse tangent of opposite, that's the negative 1.34, and adjacent 22.32. And I get negative 3.4 degrees. What does that mean? That means it's 3.4 degrees to the left, which means west of north. So, vector C is 22.36 at 3.4 degrees west of north. And that would be your final answer. So this was, it seems like a long, time-consuming process, but we went through it very slowly. And believe me, as you do these, you'll see they actually go by very quickly, but it takes a little practice. We start analytically. We have a problem. The problem gives us a few vectors. Those vectors we want to add together to get a final vector. We can't do it because those vectors are in different directions. So we're going to use a trick. The trick is, first, find the x and y components of the vectors given in the problem. How do we do it? Well, look at the vector in your mind or physically draw out the right triangle for that vector, and then use the rules of trigonometry to get the x piece and the y piece, or the x and y components of that vector, using SOHCAHTOA. Be careful, when do you use cosine, when do you use sine? That is absolutely the number one problem most people have. And as I said, the way to do it is look at the right triangle. Which side are you looking for? I want AX. Okay, AX. AX is the side adjacent to the angle, and SOHCAHTOA says adjacent goes with cosine. So it's the magnitude cosine theta. And then for y, in this case, y was the side opposite, so we used sine. Another thing to be careful about is positives and negatives. For each component, the component might be positive or it might be negative. How do you figure it out? You look at the vector. Vector A was pointing up and to the right. So his x piece is to the right, the x is positive. His y piece is up, the y is positive as well. What about B? Vector B is pointing up and to the left. Okay, the x piece is pointing to the left, so x is negative. The y piece is pointing up, so y is positive. That's the only things you're asking yourself in your head when you're trying to figure out whether this is positive or negative, is how is the vector pointing? The x component of that vector only look at the x. It's pointing to the left in the x direction, so the x one is negative. Y can be positive or negative still. They don't relate to each other. X and y are independent. All right, once you have your components all laid out, so there they are, all of our components, then to get the final answer, you add the components. So I say, okay, CX, that's AX plus BX, and you add them up. Of course, remembering there are negatives sometimes, so you leave the negatives in there. And in CY, that's AY plus BY, and you get your Y component. Then at the end, once you have the X and Y component of your final vector, you want magnitude and direction. So, let me just spell it out a little bit. Adding vectors. Number one, break all vectors into components. Add X components to get final X component. Add Y components to get final Y. Once you have it, magnitude is given by the magnitude of a vector is the x component of the vector squared plus the y component of the vector squared, all square rooted. In the direction, theta is inverse tangent of the y piece over the x piece. And that's all there is to it. Except one slight problem that happens with the direction. So, finding the magnitude, you do this process, you get the magnitude, it's always fine, as long as you did it correctly. The direction, however, sometimes may come out wrong. So let me show you an example. Let's say I did all my work and I got an x and y component of C of, let's say, The x piece is negative 3, and the y piece is 2. Okay? So, what does this look like? Well, x is negative 3, so that means it goes to the left 3. And then y is 2, so it goes up 2. Okay? And so my final vector c should look like this. That's my c. Again, x is negative 3, y is 2. Now what do I want? I want to find out what is this angle theta. Or, I want to know the direction theta. So I would say theta is inverse tangent of the y piece, cy, over the x piece, cx. So inverse tangent of 2 divided by negative 3. And when I put this in my calculator, I get negative 33.7 degrees. Well, does this make sense? Oops. I have vector c. It looks to me, it's pointing up and to the left. So there's this big old angle here, and this is something I should have said earlier. When people give you, or you give, the angle, most of the time it's standard to give the angle with respect to the positive x-axis. So, it might be 20 degrees or 180 degrees or 170 degrees. The way I drew it, where I labeled this theta, that means I'm going to tell you the angle with respect to the negative x-axis. 20 degrees north of west or something. But in general, the angle given is with respect to the x-axis. Now, look at the answer I get, negative 33.7. Well, if I were to draw that, negative 33.7 means 33.7 degrees below the x-axis. So that's something like this, where this is 33.7. Well, obviously that's not my vector c. This is some other vector. This happens sometimes, unfortunately. We did everything right. We did all our math right. We got our components. We plugged the components into the equation. Plugged that equation into our calculator. Got an answer, but the answer is wrong. Why does this happen sometimes? Well, look at this here. Notice there's no difference between this equation and this other one, negative 2 over 3. Right? Your calculator doesn't know if the negative sign is on the top or the bottom, because when it does 2 over negative 3 or negative 2 over 3, it just gives you an answer of negative 0.66666. It doesn't know that the negative's on the top or the bottom. So both of these things will give you the same answer. However, we know that these components give you this, and these components give you this. Notice this set of components is different than this one. This one says you go to the right 3 and you go down 2. That's this vector. These components up top tell you go to the left 3 and up 2. They're two completely different vectors. Yet both of these vectors give you the same answer when you try to plug it into your calculator. And again, it's because your calculator's dumb. It doesn't know the difference between the negative on top or the negative on bottom. But there's good news. The good news is, as long as you're careful, there's an easy fix. An easy fix is this. If, when you plug it in your calculator and you get this angle, you look at the angle and say, does it make sense to what I know the answer should be? In this case, it doesn't make sense. Then all you do is you add 180. So if I take that number and I add 180 to it, I get 146.3 degrees. And that's my final answer. Okay? Now this doesn't always happen. If this were the vector, if these were really the components, the bottom components, then when I stuck it in my calculator and got negative 33.7, I look at what it should be. It makes sense. 33.7 degrees down. It's in the fourth quadrant. It makes sense. I box the answer. However, in the top case, you either draw it out or you visualize it in your head. You say, what should the vector look like? I move to the left 3 and up 2. That's somewhere in the second quadrant. What answer did I get? Negative 33. That's a fourth quadrant answer. So they don't match. Every time they don't match, add 180, and that's your final answer. Okay, so that's the only caveat. Unfortunately, there's no getting around that. But this is your method for adding vectors. It works every time. You break into components, add the x's with the x's, add the y's with the y's, then you do magnitude and direction. When you do your direction, all you have to do is be careful before you box your answer, is visualize what the vector should look like, and you do it by looking at the x and y components. If they're in the same quadrant, then your answer is fine. If it's in a different quadrant, then add 180 degrees to that answer, and then you have the right answer. Okay? I hope this made sense. Believe me, this was a very long video. There's a lot of information here, especially for really only solving one real problem. But I promise you that as complicated as it might look right now, this is going to become second nature to you, and it's going to be pretty simplified after a little bit of practice. But it's critical that you practice it. You must be able to do this, because every physics problem you're about to do when we start, the very first step of everything is what we just did here. Before you do any equations, before you plug any numbers into formulas, you first do this. So if you can't do components, you're not going to get anywhere in any physics problem. So please, I'm going to post practice problems on Canvas. Look over them, practice them. If you have to, go on YouTube, look up other video lectures about how to add vectors together. Get as much practice as you can now under your belt, so that when we start into physics problems, you won't have any issues with the mathematics part. You can go straight to using equations. Okay? So look out for the practice problems I'm about to post. Again, I'll be posting the solutions as well. And as always, if you have any questions, feel free to email me. And I'll let you know if an assignment or a quiz or anything is posted as well. Until next time.